Hello, everyone. Thank you for joining us. We hope you had a good break. So my name is Iñaki Alarcón, and I'm here with my colleague, Juan Gonzalez. We're both part of the electrical studies team at the CEME. We're also here with our colleague, commercial colleague, Maria Lopez. She's here in the back. And today we'll present two cases that we've been working on. One is the analysis of reactive power regulation issues in wind farms under weak grid conditions. And the second is the development of modulation and control schemes in MMC-based STATCOMs. So we'll leave a few minutes at the end. You can ask any questions you like. So before we dive in, I'd like to briefly outline the structure of today's presentation. We'll talk about who we are at the CEME and the kind of work we do in EMTP and how this solves the challenges for reactive power regulation issues in the context of the Mexican grid code. Then we'll show a real case where we analyze a non-compliance of a wind farm under weak grid characteristics. We'll explain the problematic associated to the disturbance, and we'll share some data-driven simulations. We'll share some data-driven simulations to highlight the context of this problematic. And the third point, my colleague will explain the development of modulation and control schemes in MMC-based STATCOMs. He'll explain the STATCOM topology, the control system, and what the simulation results reveal. Finally, we'll leave some conclusions and open floor for some questions. CEME is a Mexican company focused on project development and troubleshooting in the electrical engineering field. Our work spans multiple areas of power systems. So we offer the following services. We design and build protection and control and measurement boards, often for CFE clients, which is the National Commission of Electricity here in Mexico, and also for substations, either generation or load centers. We also develop some SCADA and HMI solutions integrating modern communication protocols. And this enables us to monitor in real time the variables in substations and load centers. We have also specialized billing software, and this specialized billing software not only gives us the tariffs that CFE implies to customers, but it can also give control actions with an HMI integrated to this software. In other cases, we have also made some event and contingency analysis for our clients. We use some oscillography events and SCADA logs to analyze the root cause of the problem. Finally, our work spans through the electrical studies, and this part we do normally static type of simulations, like section coordination, short circuit, harmonic low flow, and well, this spans also to dynamic type of simulations, deliver mathematical models to SENACE, who's Mexico's grid operator, and also PPC tuning and some transient stability analysis. These are the type of applications that EMTP can offer to us, and well, here are some examples. We are working actually with the electrical study like temporary voltage transfer recovery. We have some projects that are coming, so we're exploring this type of area. We have some experience with switching transients, and practically we have a strong background on power electronics modeling and large-scale power system modeling too. So SENACE normally asks the clients or the generation facilities to deliver mathematical models of their power plants. So we make PPC tuning and integrate these models so we can deliver and make the appropriate tests. To set context in the power regulation in the Mexican grid code, it's important to note that compliance must be met by the generation facilities. In this case, we're focusing on the synchronous type of machines or the synchronous type of generation plants, and they must meet certain requirements. One of them is the power factor regulation, reactive power regulation. They must meet voltage regulation at the point of interconnection, either from direct control or QV control. They must also support contingency events and real-time monitoring and communication. So compliance is not optional. There may be fines and sanctions to the users if they don't meet these requirements in the grid code. Let's jump to the next slide. So we'll explain here an example or real power case that we analyzed. It was one of our clients who had a wind farm or wind park, and the grid operator made some observations because there were some oscillations or some voltage oscillations observed at the point of interconnection. So we had to find the root cause, if it was either the wind farm that caused these oscillations or was either the grid that caused them. So here's a figure which can be, can describe the equivalent that we're using. We're using a wind farm equivalent. Normally, STATCOMs asked us to deliver this model with some grid equivalent of subcircuits. And this wind farm is interconnected to the point of interconnection between a transmission line. This transmission line is normally more than 100 kilometers. So at this point of interconnection, normally point of common coupling, we have some main characteristics that a weak grid defines. So the main components are a low short circuit power, a high grid impedance, and since we have these two components, we can have some variations or local variations, and this can increase the sensitivity at this point. We can also, it can also be very difficult to maintain voltage and frequency stability at this point of common coupling. So we took some power measurements from our quality meter at the high voltage side of the wind farm, and we analyzed these oscillations that were produced by a transient event. These oscillations were normally around a period of 2 to 3 minutes, and they had a magnitude of around 50 kilovolts. So our client informed us that at a certain point of time, like around 1 minute after the oscillation started, there was a voltage control mode, and it does not say order to change the voltage control mode to a Q control with a reactive power of a set point of 0 megahertz. So we can see that this voltage oscillations kept on going, didn't stabilize or didn't dampen to at about 3 minutes after it started, and it stabilized around this value of 240, 238 kilovolts. So to show another variable that is important is the reactive power observed at this point. We can see oscillations of around 40 megabar. And we can also see a zoom view to see how even after that voltage or that control mode change, we can still observe the oscillations in this point. So there's some questions that we can ask us. Is the wind farm the root cause of the disturbance in the system? Well, we made an analysis of the short circuit power ratio at the point of common coupling, and it was determined that although the plant generates oscillations of 40 megabar, or is capable to generate them, it does not produce voltage oscillations of 50 kilovolts. Subsequently, it was informed that there was a disturbance in the system upstream of the wind farm, and that caused a trip of a transmission line. So that modified the topology upstream, and maybe, well, the short circuit ratio had a lower value at that point. The second question is the wind farm in compliance with the objectives established in the Mexican grid code? Well, let's find out. So we took these measurements from the power quality meter, and we subsampled these measurements, post-processed them, and entered them in EMTP for a lookup table. We then had a control voltage source at this point. So we had to include the grid impedance of the equivalent and make these considerations for entering this data input to the EMTP model. So here's on the left side is the grid or the power plant equivalent of this wind farm in EMTP. Here in this figure, we can see the grid voltage. We compare the measurement and simulation results. As we can see, this voltage, the simulated voltage, is very similar to the grid voltage that we see on measurements. But there's a quite difference on the minimum value that we got on simulation. This will be explained in the further slides. So practically, the plant was compensating reactive power, and that's why there was a minimal value different from the measured one. From the perspective of the active power, we can see that we have on blue the real or the measured values at the wind farm. We can see the variable wind speed that it's approximately the wind farm had a set point of 170 megawatts. So we can see the variations of the wind speed. And at simulation, we didn't have this input variable, so we had to set point the power point to about 170 megawatts. In this slide, we can see the reactive power at the point of common coupling. And here's the interesting part. You can see on blue the power oscillations or the reactive power oscillations that didn't dampen even the control mode was changed. So we can see in simulation that the wind farm was capable of compensating these oscillations even through the voltage control mode and even more in the control mode, the key control mode part. So here's a magnified view of this comparison between the measured value and the simulated results. We can see on green the voltage at the point of interconnection, and in blue the measurement of the reactive power. So we can see that these both measurements are in phase. And once we simulated the reactive power of the wind farm under the same conditions, we can see a reactive power compensation either on the conductive side or the reactive power side. So it's important to note that these are low frequency oscillations and have a period of around 2.62 seconds, or approximately 0.38, 0.4 hertz. On the last slide, this was the part on the voltage control mode. So as I said, the power plant was compensating the reactive power oscillations in this control mode. On the other hand, we can see that once the control mode was changed, as I said, the oscillations were dampened, and well, we can see that even the reactive power entering phase with the voltage, but these oscillations are not fully dampened, so other action must be taken into account to compensate this voltage oscillation. So here my colleague Juan will explain the development of modulation and control schemes for MMC-based STATCOMs. We had a client that he wanted to integrate, well, he wanted to compare his black box model, and he gave us that black box model. From there, we developed and tested the simulation of their MMC topology.
Okay. Thank you for the introduction, Mickey. Well, in recent years, the electrical power system of many cities have evolved. The increase of the renewable generation on solar or wind farms and the need of more flexible regulation of reactive power have driven the includes active devices like STATCOM. In this case, the STATCOM is conformed by a modular multi-level converter, and this is like is presented that some advantage like reduce harmonic distortion in this point and increase the modularity and scalability of the system, and increase high efficiency in the system with respect to other solutions, and enhance the control of active or reactive power in this point. However, this present new challenges or disadvantage, like increase or high complexity in the control and modulation of the converters, and increase the cost or the number of components that compose this system. And capacitor voltage balancing represent a great challenge for this implement, and integrate the physical size of the system. And it's important to mention with in this case study, the modular converter is composed by 14 submodules and the effects, and the nominal rate power is 50 millibars. Next, please. In this slide, show the proposed state control. We can see the other loop that the constant reactive power, and the next inner loops, the DC voltage regulator and phase balancing control, and finally the individual balancing for the current of the some converters, when each converter, sorry. And it's important to mention that the all system is simulated in EMTP, and all elements is constructed based in native or original library models in the software. Next, please. Now we can see the simulation results of the system. In this case, it's the reactive power relation at different operating steps. In these graphs, it's observed the response of the system at different changes in the reference signal at the different moments. We can see that the system, the behavior system is stacked in the different sequence steps. And other important result is of the balancing on individual voltage DC boost. Thank you. In this case, it's observed the voltage DC boost in the 14 modules in a phase, and in the zooming picture, we can see the voltage replay in each submodule. It's observed that they maintain in regulate in different cases of the set point in the system. In Quebec, we are exploring the new tools for automatization of generation of this system. My colleague Iñaki will explain more on that.
Okay, can you put the next slide? Okay, so to accelerate the process of submodule integration, what's normally a complex task, or not complex, but time-taking of instantiating and connecting all these numerous submodules in each upper and lower arm. To address this, we explored the Python API of EMTP, and we implemented some actions with JavaScript to complement an automation tool that can generate submodule instances. These based on configurable parameters like number of submodules, number of levels, arm type. And this also can connect the modules in a series with each arm and face. We can also assign identifiers and secret references to ensure the consistency of the model. And this can also validate topology even before simulation. So there's some examples, there's some tools that you can look on EMTP with JavaScript, and there's an example with HBDC with MMC topology, where we wanted to explore the Python API so we could see if it was the same task that JavaScript was that in JavaScript samples harder. So in this slide, we can see the full bridge submodule that we integrated in EMTP. This submodule was passed to a subcircuit and added to the EMTP library, so we can access it through a Python script. Here's a short Python code, short extract from the Python code that we developed and we started to explore and to, well, our objective is to make the tool that eventually you can enter the numbers of modules and connect all of the elements in an automated test. So here's a short GIF that just represents that automatic creation. So here we jump to the conclusions about section number 2. It is possible to approximate the system dynamics using real data measurements. It was determined that the root cause of the disturbance was an external event, the trip of the transmission line. We can also see that reactive power performance obtained from simulations differs from the ones in measurements. This was due to the part in simulation actually compensated the voltage oscillations. So we can also see a correct operation of the wind farm control system, and this allows us to mitigate voltage oscillations on the grid. In contrast, if we have an improper operation of the control, we can contribute to the disturbance, and this could be a point where the system destabilizes. We can also conclude that the wind farm was not able to regulate at a voltage set point, neither a reactive power set point. So there was no compliance of the grid code, and this could be, as I said before, this could turn into sanctions, fines, or maybe grid access to the wind farm. So there's some open questions. Is the voltage and reactive power regulation issue due to an incorrect tuning of the control system? Or is it just a technological limitation of the wind farm, or maybe the wind turbines? For section number 3, we have some conclusions and open questions. It is possible to implement MMC-based STATCOMs in detail in EMTP. It is possible to implement complex modulation schemes in EMTP and validate them, thus allowing us to operate the STATCOMs for reactive power regulation and any other functions. It's also possible where the STATCOM was validated at different reactive power values or set points, and this was in compliance with the Mexican regulations. So here are some references that we use for our work. And thank you for your attention. And do you have any questions?